can you solve these 6 calculus problems? We're ramping up the difficulty this week with just a week to go till paper 1 at time of release. So pause the video here, have a go at the problems, and the solutions will follow shortly. Now, our first problem is to prove that this cubic here is an increasing function for all values of x. Now, what it means by an increasing function is that the gradient is going to be positive. And in this case, the gradient is going to be positive for all values of x. So when we think about gradient, we should be thinking about differentiation, because differentiation, when we find that derivative, that is going to be our gradient function. So what we want to do is to differentiate this cubic here, and then we're going to show why that is always going to be positive. So firstly, I'm going to differentiate this cubic here. So differentiate the x cubed, that becomes 3x squared, okay, multiply by the power, take 1 off the power. The 9x squared becomes 18x, okay, 2 times the 9, take 1 from the power. 29x, when I differentiate that, it'll become 29, and when I differentiate the minus 6, that will just become 0. So I have to now prove why that is always going to be positive. And I can do this by completing the square. So what I'm going to do is I'm going to take out a 3 for the first 2 terms here. You can, if you like, take the 3 out for all 3 terms. I just prefer to do it for the first 2 terms here. And then I'm going to complete the square on the x squared plus 6x. Okay, so I want to halve the coefficient of that 6x to get 3 there. But don't forget, when you expand the x plus 3 squared, you'll get the x squared, you'll get the 6x, but you'll get an unwanted plus 9 there. So that's why I need to take away the 9. I'm keeping everything in square brackets here to make sure that all gets multiplied by 3. And don't forget, you've got this 29 that's hanging on the outside here. So what I can then do is multiply through by that 3. So 3 times minus 9 is minus 27. Add to the 29. And then we've got the plus 2 there. Okay, so that is my gradient function. But I've written it in a way that's going to make it clear to show why it's always positive. Okay, there are alternative methods than what I'm doing here, but when we've got quadratic, fine just to kind of complete the square here. So the reason why that's always going to be positive is that x plus 3 squared, well, if you square a number, it's always going to be greater than or equal to 0. Just be careful. A lot of people say when you square a number, it's always positive. That's not strictly true, because if you square 0, you get 0, which is neither positive or negative. So just be careful if you ever use logic like that in the proof. So x plus 3 in the bracket squared, that part is always going to be greater than or equal to 0. So when it comes to timesing that by 3 and then adding 2 to it, crucially, well, that always has to be positive. So the gradient is always positive. So I can say that my cubic here I can just conclude that this is an increasing function for all values of x. Okay, and that's our first question done. So the second one, so we've got something a little bit different here. So the temperature of an object after t seconds can be modelled by the following equation. Find the instantaneous rate. I had to use spell check a few times to spell that one correct. Instantaneous rate at which the object is cooling at 2 minutes. So I have a saying in my classes that when we see the word rate, we should think of the word differentiate. So that is what we're going to do here. So I can find out that rate of change for the temperature with respect to time. So what that means is I need to find d capital T by d lowercase t. Okay, I have seen in questions they have actually been picky about the notation when you do this. So don't just do dy by dx. Do make sure that you are using, not just for exams, as we should be, using the correct variables here. So when you differentiate the 20, that is going to just be 0. When it comes to differentiating e to the power of something, well, if it's just a t here, it's not like t squared or anything like that, what we can do is just simply multiply by the coefficient of minus t over 90. So that would just be minus 1 over 90. So I times that 50 by the minus 1 over 90. And I just keep the e to the power bit as it is. Okay, if it's something a bit more complicated, as we've seen in previous videos, we can use the chain rule in which to differentiate, but that shouldn't be necessary here. We can just say, okay, well, I times the 50 by minus 1 over 90. Okay, remember, this isn't just simple as take 1 off the power, multiply by the power, take 1 off the power. Okay, different rules when we've got e. So we've got 50 times minus 90, that's just minus 5 over 9. And then this e part will just stay as it is. So we want to find the rate at which the object is cooling at 2 minutes. So this is the, for any value of t, this will be the rate at which the temperature is changing. So we want to find, well, at the instance, at 2 minutes, what is that going to be? Now, just be careful, because we're told that this is after t seconds, but I want to find it after 2 minutes. So I don't want to sub in t equals 2, I want to sub in t equals 120. So I substitute t equals 120 into this, so into my derivative here. Which, when you process this on a calculator, you'll get minus 0.146. So the question is to find the rate at which the object is cooling. So we just need to be careful how we actually phrase our final answer. So we can say it's cooling at a rate. Now, because we're talking about cooling, we're implying the negative already. So when I leave this answer, I'm going to leave it as a positive number. Now, when I calculate it, I get the negative, which is implying that it is cooling. But when I'm asked to find the rate at which it's cooling, I don't want to give a negative here, because the negative is already implied by the fact that we're saying it's cooling. So I'll leave it as a positive 0.146. Okay, it's a bit like you wouldn't ever say that you're minus 20 pounds overdrawn. Okay, you would just say 20 pounds overdrawn, for example. The last thing I'm just going to do is put some units on this. So I was doing dt, d capital T, by d lowercase t. So what I want to do is just, with my units, I'm doing degrees divided by time, which is in seconds. So this would be, you'd lose, sorry, not seconds, just seconds, would just be 0.146 degrees per second. Okay, so probably these first two, not too bad. We're going to kind of pick up a bit with this third one, not going to lie. this is where it's going to get a little bit more complicated. But to be fair, this is based off a question from a past paper, quite a similar style one. So I thought I'd share this one with you. So we've got x to the power of 4 sine 2y equals 4. We're given that y is an acute angle essentially, okay, so between 0 and pi over 2. And we need to show that dy by dx somehow ends up as the following there on your screen. So it does seem quite different to what we started out with. Now, when I've got a mixture of x's and y's, or just two different variables in particular, and it's not easy to make either x or y the subject, I want to be thinking about implicit differentiation. Okay, so when it's not either way, it's not possible or it's not going to be simple to make x or y the subject, we should be thinking about using implicit differentiation here. So we'll come on to how we use that as we go through the problem. So we start off with our left hand side here, and I'm going to differentiate this left hand side. Now I have a function of x times a function of y. So if I've got a function times a function and I can't simplify it, I need to be thinking product rule. Okay, so not only are we going to discuss implicit differentiation here, we're also going to get in some product rule as well. So I'm going to call u x to the power of 4, and I'm going to call v sine 2y. Okay, so to do the product rule, I need to differentiate both of these. So du by dx, well, this one should be fairly routine. Okay, that just becomes 4x cubed. But if I want to find dv by dx for my product rule, well, when I try to differentiate something that's got a y in there, this is where the implicit differentiation comes in. So what we do is differentiate the sine 2y with respect to y. So that just becomes 2 cos 2y. Don't forget to multiply by the 2 there. But because I've differentiated that with respect to y, I'm going to need to multiply it by dy by dx. Okay, because I'm actually trying to differentiate v with respect to x. So if I differentiate it with respect to y, that is okay, so long as I multiply by dy by dx. So now we can apply the product rule. So I'm going to do the x to the power of 4 times the 2 cos 2y times dy by dx. Okay, so doing the first function times the second one differentiated. Actually, let's put that 2 at the front there. So 2x to the power of 4 cos 2y dy by dx. And then I do the second function the first function differentiated times the second function. Well, that will give me 4x cubed sine 2y. Now, so far, I've differentiated the left-hand side. What I also need to do here is differentiate the right-hand side with respect to x. Well, if I differentiate a 4, that just becomes 0. One thing that people sometimes forget with this is they sometimes just differentiate one of the sides and just leave it as an expression, where it's crucial that we still keep this as an equation when we're doing this. Okay, so make sure that you're keeping it in the form of an equation and you're differentiating both the left and right hand side here. Now we want to get dy by dx, so what I'm going to do is take away 4x cubed sine 2y from both sides, and then I'm going to divide both sides by 2x to the power of 4 cos 2y. So we're going to take away, just going to do this in one step, but we're going to take away 4x cubed sine 2y from both sides, and then I'm going to divide both sides by 2x to the power of 4 cos 2y. Okay, so the goal there was to try and get dy by dx on its own. Sometimes you'll see problems with multiple dy by dx's, in which case you'll need to get all of them onto one side and then factorize there. Okay, so that's dy by dx, but it's nowhere near what we're being asked to show, unfortunately. Okay, so, in the exam we'd get some credit for getting this far, but we wouldn't get the full credit for getting it in this form here. So there are quite a few ways that we can simplify. You can actually, some of you might be thinking, okay, sine 2y divided by cos 2y, I can just make that tan 2y. You can do that. I tried doing it that way, and it pretty much just works out about the same sort of level of work as what I'm about to show you, but you can do that if you wish. Okay, but the key thing here is we've still got y's on our answer, whereas what we're being asked to show is entirely in terms of x. Okay, so we need to do some work on this to get this all in terms of x. Now, one thing we can do quite quickly is just simply say that, well, 4 divided by 2 is 2, and x cubed divided by x is just going to leave us with an x on the bottom here. So let's just do that part first, and then we'll deal with these sine 2y's and cos 2y's. Okay, so all I've done there so far, just 4 divided by 2 is 2, x cubed divided by x power 4 just leaves us with an x on the bottom there. Okay, so what I want to do is write sine 2y and cos 2y in terms of x. The sine 2y isn't too difficult to get there, because if I notice from the start of the question, x to the power of 4 sine 2y equals 4. Well, therefore, sine 2y is just the same as 4 divided by x to the power of 4. So that's useful. I can now just replace sine 2y with 4 over x to the power of 4, and now everything is in terms of x, for the sine 2y at least. Cos 2y, that's going to be a little bit more work that we're going to have to do, but we can cope. Now, from my trig identities, I know that sine squared plus cos squared equals 1. So I can rewrite that as cos squared 2y is 1 minus sine squared 2y. Okay, maybe we've got to keep this angle the same when you use that identity. So cos squared 2y will be 1 minus sine squared 2y, but I've already worked out that sine 2y is 4 over x power 4. So sine squared 2y will be 16 over x to the power of 8. Okay, I'm just simply squaring my result for the sine 2y there. Okay, sine 2y is 4 over x power of 4. Sine squared is 16 over x power of 8. So what I've got there is a result for cos squared 2y. So cos 2y will just be the square root of all of this. Okay, but it's the square root of all of this. It's not just, you can't just square root the individual terms. That's probably one of the biggest misconceptions I constantly see throughout A-level maths. People just square rooting individual terms. You have to square root the whole of that side. You can't just say, oh, it's just 1 over, 4 over x power 4. It doesn't work like that. You have to square the whole of that right hand side. Okay, so brilliant. We now have written sine 2y and cos 2y in terms of x. So let's now go back to this dy by dx and start subbing this all in. So the sine 2y gets replaced with 4 over x to the power of 4. And the cos 2y gets replaced with 1 over 16 square root of 1 minus 16 over x to the power of 8. So it looks like we're getting there, but not quite. Okay, let's make this a bit smaller. These problems originally were just going to be nice little quick simple ones, and then I've clearly got too excited over these weeks and started making them a bit harder. So, nearly done now. So what I can then do is just I'll tidy this up a little bit because we still haven't quite got it in the form we're looking for. So minus 2 times 4 is minus 8. And I can divide by that x to the power of 4. So I've just got x to the power of 5 now on my denominator. Okay, so we've got the minus 8 on top. Brilliant. Not quite got, though, the denominator correct. So let's look at how we can deal with that. Probably going to have to do a couple more steps. So in this square root bit, I can see I've got 1 minus something. The answer is x to the power of 8 minus 16. So what I'm going to do is I'm going to take out a 1 over x to the power of 8. Okay, I'm going to take out a 1 over x to the power of 8. So what that means is the 1, to get the 1 back, I'd have to times the 1 over x to the power of 8 by x to the power of 8. Okay, because that will make 1. And then to make the 16 over x to the power of 8, I need times the 1 over x to the power of 8 by a 16. And then we're pretty much there. Because if using the laws of surds, square root of a times square root of b is the square root of a times b. So I can separate this out into square root of 1 over x to the power of 8 times the square root of x to the power of 8 minus 16. And the square root of 1 over x to the power of 8 will just be 1 over x to the power of 4. So x to the power of 5 times by 1 over x to the power of 4 will just be x. And then you've just got the x to the power of 8 minus 16 there. Now, I will say, especially with it just being 1 week till the first exam, if you get a question like that and you're really struggling to get it in the kind of final form, please don't waste your whole exam time trying to get it in that form, because typically it might only be worth 2, 3, maybe most 4 marks, depending on what the difficulty of the question is. You know, if you're spending 20 minutes trying to do it, then maybe your time is better spent on other questions in the exam. By all means, do the differentiation part, get that bit. If you are struggling getting that final form, hopefully this has helped, but please don't spend ages and ages on it like I sometimes see some students do. Okay, so just a little bit of the tips there. Okay, so that got a bit more harder, didn't it, than the first two? Let's have a look at question number 4 then. We're going to get into some integration now. So we're given that the value of this integral is 7 over 2. We need to find what a is. Okay, so let's look at how we're going to do that. So these problems do come up quite a bit where you have to integrate. You're given the result here and you need to find a missing constant. So they do like these questions from time to time. So how we should approach them is do the integration as we normally do, sum in our limits even though we don't know what one of them is, and then just set it equal to, in this case, 7/2. So the first thing we're going to need to do is to integrate this. So the first thing I want to do is to just rewrite the problem. So rather than have it as 1 over the cube root of 9x minus 1, I'm going to write it as 9x minus 1 to the power of minus a third. So now I'm going to integrate this. Yeah, again, you might have quicker ways of getting here, but I'm going to do just a kind of like it's sort of trial and error, but with a bit more sort of logic, just kind of randomly guessing numbers. Okay, we're going to think, well, we've got 9x minus 1 to the power of minus a third. Let's try that with a higher power. Okay, but when I say a higher power, I'm going to try something with a power that's been raised by 1. So minus a third plus 1 is 2/3. So let's just differentiate this. I'm going to check that via the chain rule. We know we love the chain rule here just to do our nice little checks. But as I say, if you can do it quicker, that's fine. But if in doubt, use the chain rule. So replace the bit in the bracket with the u, and then work out dy by du, work out du by dx, and then I multiply these together. So 2/3 times 9 is 6, and then pop your u, pop that 9x minus 1 back in, and we can see if we try 9x minus 1 to the power of 2/3, when we differentiate there we get 6 there. So what that means is that when I integrate 6 times 9x minus 1 to the power of minus a third, that's going to give me 9x minus 1 to the power of 2/3. So that's not what I'm actually trying to integrate. There's no 6 there. There's just simply a 1 in front of the bracket. So to compensate for that, what it means is when I integrate 9x minus 1, I need to adjust for the fact that there needs to be a 6th on the outside here. So I'm going to put this result into some square brackets here. Okay, so that is the result of integrating 9x minus 1 to the power of minus a third. Okay, it'd be 9x minus 1 to the power of 2/3 multiplied by a 6th. Now, because I've integrated it, I'm going to put that result in some square brackets here. I'm going to take the 6th on the outside just because it's constant and I can do that. Please don't do that with any x's or anything, your variables or anything like that. For the constants, you can simply take them on the outside just to make it a little bit simpler. So that is equal to 7/2. And what I can then do is just multiply both sides by the 6 there. So 6 times 7/2, give 21. Okay, and then what I'm going to do is start plugging in my limits. So I'm going to substitute in the a first. So that'll give me 9a minus 1 to the power of 2/3. I'm going to substitute in the 1. So 9 times 1, take away 1 is 8. Do that to the power of 2/3. Cube root of 8 is 2. Square it for 4. And remember, I have to take away that lower limit. So I know that when I sub in the limits, that should be equal to 21. I'm going to add the 4 to both sides. And what we want to do is we want to find out what a is. So I'm going to, actually I don't need the brackets anymore. I'm going to do both. We're going to take both sides to the power of 3 over 2 to get rid of the 2/3 there. Okay, so I'm just doing both sides to the power of 3 over 2. 25 to the power of 3 over 2 is 125. Okay, square root 25 is 5, cube it 125. Then add 1 to the 125, divided by 9. And we've got 14 there. Alright then, question 5. There will be a few different approaches that you could take to this. I'm going to go for a substitution, but some of you might go for parts with this, which will also work just as fine. But I want to do a little bit more of a substitution, just show you another one you could do with that method. So that's what I'm going to do. So my substitution is going to be to let u equal 2x minus 3. So I'm going to let the bit in the bracket, which typically is usually what you end up doing with a lot of substitution problems, I'm going to let that bit in the bracket equal u here. Okay, so if you want to pause it now and try it with that substitution, feel free. Parts will work fine as well, but just want to show you another one with substitution. Okay, so when I substitute, what I always recommend that you do is find the derivative of your substitution. Okay, because you will need that in terms of helping you replace the dx, because when we do a substitution we want to get rid of the previous variable and have it all in terms of our new variable, and that includes replacing your dx with a du, or d theta, whatever variable you choose. Sometimes you'll actually spot the du by dx within it. Okay, not here, but occasionally that does happen. So what that means is we can replace the bit in the bracket with a u. We can rearrange du by dx equals 2 to get dx equals a half du. Okay, so I can now replace the bit in the bracket with a u. I can replace the dx. The only thing left to replace is the x. Okay, so what I can do is go back to that substitution of u equals 2x minus 3. Add 3 to both sides and divide by 2. So I can rewrite x as u plus 3 over 2. Now what I can do is replace the x with the u plus 3 over 2. Okay, all the x's must go. They need to get replaced with u's here. So x gets replaced with u plus 3 over 2. We've got a u to the power of 5, okay, just replacing the bracket, what's in the bracket with a u, and that's being taken to the power of 5. And your dx gets replaced with a half du. And it's kind of weird with what I've done in the brackets, but I'm trying to just show you how we kind of replace each bit by bit. So what I can then do is just start multiplying this all together. So we've got u over 2 times u to the power of 5 times a half here. That's going to be 1 over u to the power of 6. Then you've got 3 over 2 times u to the power of 5 times a half. So that's going to be 3 over 4 times u to the power of 5. Okay. And then we've got something that's much simpler to evaluate. Okay, all I need to do here to the u's here is add 1 to the power. So u to the power of 7, divide by the new power, 1 over 28. And then again, add 1 to the power, u to the power of 6, divide by the new power, 3 over 24, and then plus c. Finally, we just need to pop our substitution back in, so we have it in terms of x. And of course, we're not even daring to forget r plus c here, of course. And we have our final result. You can you could simplify this a little bit further if you wanted to, but I'm just going to leave it like that for now. All right, final question then. And I'm actually interested. I've got a way that I'm going to do it, but I'm really interested to see if you have a different way that you might do this. Okay, I'm going to show the way I would tackle this one, but please feel free to send me your suggestions how you would do this, because I think there will be a number of different ways in which you could achieve the final result here. Okay, so we've just got to integrate tan to the power of 4. Doesn't sound like it's going to be too hard, but as I've said before, with integration it is much harder than differentiation. We can't just simply do the reverse of what we do with differentiation here, which would be just, oh, I multiply by the power, multiply by the derivative of the bracket, reduce the power by 1. Okay, it's not like you can just, add 1 to the power, divide by the derivative of tan. Doesn't quite work like that. Okay, so with lots of different approaches, this is the approach that I'm going to take. And if at any point you kind of think, okay, I could take it from here, feel free to pause and see how you get on. Now I'm going to rewrite tan to the power of 4 as tan squared times tan squared. Okay, so I'm going to rewrite tan to the power of 4 as tan squared times tan squared. Now, tan squared is the same as sec squared minus 1. Okay, so that's just from your trig identities that you should have learned in year 13, that if you have 1 plus tan squared, that is sec squared, and just rearranging that. Okay, now I'm then going to multiply this all out to give me the following. And then, what have I done there? Sorry, tan squared x. Okay, so I'm going to multiply that all out, and then what I'm going to do is I'm going to rewrite the tan squared again using that identity that is sec squared minus 1. Okay, and then I'm just going to just times that bracket out by the negative 1. Okay, so I've done all this because I wanted to get separate terms that I could integrate with not too much fuss. Now, the last two hopefully look like they are something that you can integrate with relatively ease. Hopefully you can integrate 1 by this point. I think if you got to this far in the video, I think you're the type of person that can integrate just a 1 on its own. Sec squared, remember, that is in our formula book. So when we integrate sec squared, we're going to get tan. The one that's probably a bit more harder to spot is how we integrate sec squared times tan squared. As I said before, integration is a bit weird in that integrating tan squared by tan squared, I can't just do that right away, but sec squared times tan squared, we can recognise something that would be a good thing to try here and get us close to the answer. Now, what I would be recognising with sec squared times tan squared is that when I differentiate tan, I get sec squared. So because the derivative of one of the functions is what I'm multiplying by, then that would lead me to think, well, let's try tan to the power of 3. Because if I differentiate tan, I get the sec squared. So that then leads me to think, well, let's try tan cubed as a potential answer here. So one more time, I'm going to use the chain rule here to see what this would differentiate to be. So y is going to be u cubed, where the u is tan x. Because remember, tan cubed is just tan x in the bracket to the power of 3. So when you differentiate tan, you get sec squared as mentioned before. So when I differentiate tan cubed, I get 3 times u squared, where the u squared is going to be tan squared. Okay, so when I differentiate tan cubed, I get 3 tan squared sec squared, which is nearly just sec squared tan squared, except for I end up with a 3 in front of it. So that means that integrating 3 tan squared sec squared would give you tan cubed. So if it's just a single sec squared tan squared, the answer will just be a third. So integrating sec squared tan squared is a third tan cubed. Integrating sec squared is tan x. It's in your formula book. Integrate the 1, it's just x. And finally, we have the plus c. But as mentioned, I'm interested to see if you've done that a different way, because there will be different ways that you could approach that. So interested to see that. Probably went a bit more difficult with some of these ones at the end. Did intend at the start of these videos to be kind of quick, slightly quicker than this. But I think I just thought, well, we'll delve into some harder stuff, really getting you prepped for the exams that are upcoming. I'll try and scale it back a little bit, not give you anything too overwhelming ahead of paper 1. So I'll try and put that video out for next Monday. And then based on that, we can then, based on the paper 1 that comes out, I'll try and tailor the following week to more just looking at what's more likely to come in paper 2, and then even do a applied edition in a few weeks' time ahead of paper 3 as well. But let me know if there's anything in particular you'd like to see either more of, less of, or any sort of particular ways you've done it.